All right. We're about to get started here. Um, we'll give it a couple more seconds, maybe a minute, to see if anyone trickles in after 11. But welcome everyone to our webinar. Excited to be learning about some soft robotics with you all today. So, um, yeah, let's get started. So my name is Matthew. I'm the technical support specialist here at Voltera. And today we will be learning about the field of soft robotics and how Voltera's Nova can enable printing electronics for these soft robotics. I'm lucky enough to be joined by an expert in the field of soft robotics, Nick Levinski. He's currently the Wearable Mechanical Engineer at Proception AI, but he also did his master's at UW studying some of the soft robotics field. You may recognize him from our video announcing Nova's planned feature earlier this year. So that's pretty fun. Before we get started, I'd like to do a quick survey on everyone's experience with soft robotics. This will just gauge kind of where we're all at in our knowledge of the field. And I'll open the survey for about 30 seconds to a minute, and we'll be able to see the results once it's ready. So let's see if I can launch this. So you should see the survey pop up now. And we'll get to see everyone's answers on where they are at. All right, so if I end this and share the results, we should be able to see everyone's results. So yeah, most of us are new to the topic or just have a basic knowledge of soft robotics, with some people that have a bit more knowledge, so that's great. We'll all be able to learn something today. So, what are we going to cover today? So today's webinar will be split into four main sections. First, Nick will explain what soft robotics are and some of the work that he's done in the field. He'll then talk about some of the exciting opportunities flexible robotics and soft robotics offers for the future. I'll then be giving an overview of Nova, Voltera's material dispensing system, which is designed for prototyping flexible, stretchable, and soft electronics. We'll then dive into some of the specific materials, substrates, and methods that you can use with Nova to print soft robotics. We'll showcase some of the prints our team has done, our applications team has done that could be translated into soft robotics. And finally, there will be some time for you to ask Nick and I questions about soft robotics and Nova. Also, stick around to the end of the webinar. We'll have a $2,000 discount code that you can use for purchasing Nova. So I will let Nick take it away from here to give us some information on soft robotics.
Thank you very much for the introduction. Hello, everyone. My name is Nick Levinski, and today I'll be presenting some previous projects and some information on soft robotics and soft sensing. So let's get into it. So we're going to go over the background of soft robotics, primarily what is soft robotics, some of the applications, how sensing kind of intertwines with soft robotics, some of my previous projects, and some new trends and some insights that I've seen kind of going on in the industry. So my background, previously I researched stretchable capacitive sensors for lymphedema monitoring. That was my main thesis work. I collaborated on many soft robotics research projects ranging from grippers to medical devices. And this is all done at the Waterloo Microfluidics Laboratory. And currently now I'm working at Proception AI building dexterous robots. So what is soft robotics? Soft robotics is a field of robotics focusing on building machines from compliant, deformable materials such as silicone, elastomers, and fabrics. They're often inspired by biological systems such as octopuses, worms, and then human muscles also a lot of times. And they prioritize safe interaction with humans and delicate objects due to the inherent softness and flexibility, allowing them to adapt to different objects and different environments. These can be used in areas like medical devices, wearable assistive tech, search and rescue, and agriculture, and many more. So we'll get into that a little later. Now, talking about the fundamentals of soft robotics, they can kind of be broken up into some discrete classes where people focus on different parts of it. The most common side is actuators. So different type of actuators that can give different responses and that can be driven by different types of stimulus. Then we can look at controls and how we actually can allow these systems to work effectively in environments and efficiently. And then sensors, which are a crucial part, in my opinion, on the topic of soft robotics and how we can accurately control them and make them even more adaptable and usable for different environments. And then modeling and manufacturing. And this is a very difficult component of it. And there's a lot of work still being done in that field. A brief overview, kind of how to differentiate these from maybe traditional robots that you've seen around you or you've seen on the internet. Um, I guess most of the traditional robots you'd see in automotive manufacturing is a commonplace, and these are non-redundant systems. They are programmed, and the robot will do exactly as it's programmed to do, and there's no redundancy in this, basically. So if there's any misalignment or problems with the object you're trying to grasp, there's going to be some problems. And then there's some now redundancy built into some new robotic arms that allow them to be back drivable. So they're a little bit safer and they can kind of adapt a little bit more to their environment. And then as we kind of shift forward more to the right, we go into these hyper redundant or continuum systems where, because of their compliant nature in both their actuation and their materials, they can be even more safe and more adaptable, where slight misalignments or changes in the object shape can still be easily achieved and handled effectively. And now going into some specific actuators. So the main one that is often used or is commonly used right now is pressure driven. So these are pneumatic networks, artificial muscles, bellow actuators, and these are common ones that I've worked with in the past. And there's continuously more research efforts to develop new ones. And so magnetic soft robotic actuators exist, electric, thermal, and now soft rigid hybrid have become very popular as well. And even more ways to control soft robots are being invented every year. And so it's a really exciting field to see all of the ingenious ways and methods. So going into pressure driven, which is probably one of the more common ones, there's McKibben muscles, which are often considered the first soft robot. They're quite old, actually, and they provide high tensile forces while remaining lightweight. Pneumatic networks are continuous soft robots, so they're often made out of one continuous material, and they naturally provide a bending actuation, making them super applicable for gripping and grasping applications. And then we have bellow actuators, which I've worked with a lot in the past. And these ones are basically very compact soft robotic systems that can fold down to a very small package and have very large stroke lengths. So for lightweight systems where you want to have a large working range, these are really great little actuators. And then a very popular trend right now is mechanical hybrids. So these are basically leveraging rigid and commercially available motors or servos, so traditional driving systems, but then use a elasticity from either the end effector material or the power transmission. So think about almost a rubber band that is pulling on these fingers in this example here. So that allows you to add basically passive compliance while still leveraging the controls of traditional motors and servos. And so these are really exciting and can kind of solve a lot of the more challenging manufacturing issues that a full soft robotic system might have. And then going into modeling now, so this is an extremely complex part of it. And the main reason is that a fully soft robotic system has almost infinite degrees of freedom. And they're non-linear in their materials, often requiring hyperelastic models. And because they have such large deformations, there's almost different models you need for each regimen of deformation. And the strong coupling between the driving forces and as well as the material deformation makes this a really hard challenge. And so lots of work is being put into modeling. And this can also kind of tie into some of the discussion later and why this can really increase the weight on sensors. And then talking about soft sensors, basically these allow us to have real-time feedback. And we're going to talk more about sensors that are integrated into the system itself, because you can run some of these robotic arms or soft robots based on image or computer vision. But we want to talk a little bit more about embedded sensors. And so these are durable, they're closed loop control, so you can actually understand what the soft robot is doing in different environments. And this helps you with being even more adaptable and kind of reduces the importance of modeling in a lot of ways because we can't really create perfect state machines or control systems that know exactly what this robot is going to do. And so talking about different types of sensing, the popular ones are resistive, inductive, capacitive, and triboelectric. All of these can be formed into a kind of planar fabrication systems. They're all still being heavily researched, and all of them provide different pros and cons, depending on material costs, material safety, and what kind of electrical resulting signal you're getting out of them. And so that can change how you actually can measure these systems and how easy it is to process those signals. And now, kind of going into some of the previous research that came out of the Waterloo Microfluidics Laboratory, I didn't directly contribute to these projects, but I was around when they were kind of being developed. And so you can see a single soft rigid hybrid joint that was developed by some really smart researchers at the lab. And so this allows you to leverage traditional rigid robots, but also have natural compliance because this is a pneumatically driven system. And then you have a high degree of freedom, hybrid hand. So this is a really cool project. We're using those bellow actuators to articulate and move this hand so it can grasp different objects. So it's a really cool project I wanted to highlight. Um, and now going into one of my personal projects that I worked on at the lab, and this was a additively manufactured soft gripper. And so we wanted to create a 3D printed soft robot, which has its own set of challenges. We wanted to integrate flexible force and bending sensors so we could better understand how we're grasping objects and control this system better, and then integrate the two of them together because a soft gripper by itself is pretty hard to understand how much pressure you want to drive it with. So the combination of the two could lead to some promising results. And so first talking about the gripper itself. So this was a single construction design. So we want to make this so it's almost like a one-shot fabrication. A lot of research grade soft robots require quite extensive manufacturing. So leveraging 3D printed silicone is a really exciting opportunity, but it provides its own challenges. So to access that faster iteration and like low development costs that 3D printing provides, you have to address some other challenges. So first we went through and did some basic modeling to understand how we can optimize the geometry of this soft robotic element, the bending actuator inside of it, so that it could be really high displacement, but still small internal volume. And that's important for when we start going into how we're going to additively manufacture this. And so there was some preliminary simulation and analysis done to understand how we can change the internal structure of this soft robotic gripper to make it so that it could be 3D printed. And so there is a lot of really interesting work done on this and changing different lattice geometries that are stiff in one dimension, but very elastic and flexible in another dimension. So these kind of enable you to print it in the top-down stereolithography manner, but still can bend and actuate in an efficient manner. And then looking at kind of the final proposed design for how we're going to integrate sensors into this. So we want to understand the force that this soft gripper is exerting on that end piece, on whatever object it's grasping. And we kind of want to understand what angle it's bending at so we can drive that pressure into the system a little bit more effectively. And so we chose to use a capacitive force sensor and a capacitive bend sensor, which is essentially a capacitive strain gauge. And so we came up with two different designs and we were kind of weighing the different options. And so this was developed with the Nova system. And we had a three-layer deposition, but that introduced a fold line. So we had to have to fold the sensor over to kind of complete that force sensor element. Or we'd have a four-layer deposition, which was a little more challenging because you had to do even more multi-layer printing. But we ended up going with the four-layer deposition because we were really worried about getting that fold line and that crease down in a way that wouldn't destroy that electrical connection. And it ended up turning out pretty good. So this was actually printed on the Nova, and it doesn't have the top encapsulation layer, and the main reason is just that it's easier to see what's going on with the sensor. But you could imagine that there'd be another translucent or opaque insulating material that's put on top of this. And so this is done with a stretchable silver ink and another insulating ink from ACI. And so it worked out quite well. And now one of the hardest problems with soft robotics and integrating soft sensors is how you actually integrate the two of them together. And so we chose to use a glove system. And this basically allows you to have a simple fabric outer shape that's out of an elastic fabric, so something like spandex or lycra. And you can basically heat press a lot of TPU substrates onto this fabric. And that allows you to couple these two systems without trying to bond to silicone, which bonding to silicone can be really difficult. and it allows you to kind of blur the mismatch in material properties quite a bit. And so this doesn't require any additional adhesive, and it's compatible with a lot of different materials and substrates. Basically, most TPUs can be heat pressed, and a lot of fabrics can as well. And so here's the end result of the project. It was pretty effective, and I thought it worked out pretty well. And now we're going to go into another project quickly. I know we're going through this fast, but a little bit of a background into lymphedema. So this main project was trying to address some of the symptoms and the treatment of lymphedema. And so that's the dysfunction of the lymphatic system. So essentially, your body cannot pump lymph fluid anymore, and this causes accumulation. And the primary way to treat this is with manual lymphatic drainage, which is a very specialized massage method that has to be done by a trained physician. And so that's not necessarily accessible to everyone, and you can't really reliably get that treatment in a portable, on-the-go fashion. And so what we set out to develop, our group, was a portable system that was very lightweight and low cost that could basically provide this specialized um, massage technique to help push that lymph fluid back into your body away from your limbs. And so this was a really interesting project combining both microfluidics and soft robotic actuators. And so for the microfluidic side, it's basically a chip that controls the whole system. And this is a passive design because there's not really any additional solenoids or electronics running in this. This is just a restrictive flow microfluidic chip that allows you to have sequential inflation of your different soft robotic elements that are applying pressure to your arm without having any heavy or bulky electronics. And so, again, kind of going back into the modeling side of things, modeling is very difficult. And so when you simulate this design, you get a really different result from what you get in reality. And so that could be that at the time the modeling methods weren't ideal, but it's quite a hard dynamic system to take into account all of the different responses and elements and physics going on. And so that's kind of a key takeaway is that the modeling is still a very developing component of soft robotics. And so having sensors can really help reduce some of that overhead that is required to get a model right. And so looking at how this was actually integrated, so you can see a microfluidic chip hanging off of this a really early version, and then some different textile integration with some strain limiting regions to help kind of concentrate that force onto the arm. And then with some of the later iterations, we had a really sleek package. And these are basically all little soft robotic bladders. So just basically an air bladder that's applying a compressive force onto your arm or other limb when a pneumatic pressure is applied to them. And then looking at the pressure profile that we got, it looks a little bit discontinuous. There's a lot of gaps in it, and it's pretty challenging to really understand what's going on and how to effectively assess our system. And that's because at the time, commercial sensors were pretty rigid. Even the top of the line sensors, these still great sensors, they really aren't designed for this. So I don't want to really bash on these sensors that were developed by quite a large company, but they have some problems, and there's not really any accessible sensors out there right now. So that's why I want to really emphasize the need for developing these different sensors that can be applied to compliant or deformable surfaces like a human limb. And because these are basically like a rigid sensor that's just kind of flexible, you get all these discontinuities, and it's pretty hard to really take the output values as a truth. So yeah, that's kind of some of the challenges we faced, and that drove a lot of the kind of research into sensors, started that in our lab. And now going back into some other applications, so a huge one right now that's actually deployed in the market is food and packaging. And so this can address labor shortages, but a lot of times with food, there's differences in the food shape and even packaging shape. And so soft robots can basically allow you to have one robot that can handle all different types of object geometries. And so this allows you to have pretty small scale fabrication and small scale assembly lines that are still adaptable and don't require specialized tooling for every time a product changes or if you have to change what's going on the line. And a key aspect of soft robotics as well is that they have reduced contamination because many times they're almost hermetically sealed, they're airtight, so you can wash them, and they're made out of silicone, so they're pretty easy to wash and sterilize between different types of food batches. Some of the emerging opportunities are medical robots, which I find are really interesting. And these are non-destructive, and they can kind of harness natural pathways that already exist within your body to kind of control the locomotion. So as opposed to having kind of a rigid catheter system, you can have a soft catheter like surgical tools for minimally invasive procedures. And these materials can be sterilizable again because of that silicone, or a lot of these elastomers can be just completely cleaned without having any degradation to the material. They're often biodegradable, biocompatible, and we can employ safe patient contact. And that's a huge part, is that you can reduce some of that pressure on the surgeon from damaging soft tissue systems. One of the really exciting things, in my opinion, is rehabilitation and wearable treatments. And so that kind of ties into the previous lymphedema treatment sleeve that we had um, at the lab. And so a really great example of this is actually a soft robotic rehabilitation glove made out of the WIS Institute. And so this was for post-stroke rehabilitation, where the soft robotic glove can apply forces onto your hand to basically aid the patient into recovering some mobility in their hand without having any chance of harming them. Because it's a completely soft system, it can't really overpower anyone, but it still allows them to guide the hand into proper postures and to allow portable and like patient-centric therapy and rehabilitation, which I think is a really great application of soft robotics. And now looking at the future outlook, sorry. Soft robotics is expanding rapidly, and it's not just growing in size, but it's branching into a lot of new markets, and it's looking at kind of pushing past that, oh, it's purely soft. So looking at both hard and soft hybrid systems, where these hybrid systems are becoming increasingly popular, offering the best of both worlds, allowing kind of more simplistic controls, simplistic fabrication, where you can just really focus on making each specific element more like traditional robots, as opposed to trying to develop a completely soft system like a lot of the early soft robots. So that allows you to scale this fabrication and then allow them to be kind of customized for different applications, even in a more effective way. And then at the same time, deep learning and like deep integration of sensors themselves can really push past some of those difficulties in modeling and controls. And so that's like a really big limitation, is that modeling and simulating these systems is quite complex, but having sensors integrated, as well as some of these really advancing reinforcement learning models or AI models, can help kind of bridge that gap, where we can kind of jump past that in a lot of ways, where modeling can still drive a lot of design decisions, but it doesn't really need to be fully incorporated into the controls. And so that's really exciting. And I think that the future is really bright for soft robotics, and I'm really excited to see all of the different applications that keep coming out of research and even in the industry. And yeah, where soft robotics looks and lies in the next couple of years. So I'll pass it back over to Matthew. Thank you very much, everyone, for listening to the presentation.
Thanks, Nick. That's awesome. Some great information on what you've done and on what the industry is kind of looking like currently and in the future. So we're going to go ahead and dive into a little bit of an overview on what Nova is. Just before that, I want to highlight, I know some of you have been using it, but we do have a Q&A section. This is where you can answer or ask some questions that you have as we're going through. We do have some of my colleagues from Voltera in the chat that will be answering some of those questions, and then if those aren't answered through them, we will go over some of them at the end in the Q&A section. But feel free to ask your questions as you think of them in there, and then we'll address those at the end. So what is Nova? Nova is Voltera's benchtop modular dispensing system. It allows you to create printed electronics right on your benchtop. It streamlines research and development with direct ink right dispensing, and this is unlike traditional screen printing. where there's no tooling, no waste, and no cleanup. Intelligent material calibration and design alignment can allow you to accelerate your workflows, and you can configure Nova to your needs with quick swap modules and work area. Nova's Smart Probe enables Nova to create an extremely detailed height map of the surface of your substrate. It uses a high accuracy ruby tip stylus and internal carbon resistor sensors to detect surface height changes and topology. If you increase your probe touch points, this will give you even more mapping resolution, so you have control over your height map resolution. Nova's Smart Dispenser is what allows Nova to dispense inks. It uses positive displacement with accurate fluid pressure sensing to dispense high resolution features down to 100 micron trace widths, and even smaller is still achievable depending on the material you use and the nozzle sizes. The Smart Dispenser has a built-in heater that stabilizes the viscosity of your ink, and so it's compatible with a wide range of materials. Nova has an onboard camera. This onboard camera allows you to inspect and align with around 17 micron per pixel resolution. You can capture images to measure pass spacing and trace width down to the pixel, and you can easily scan your prints for quality control after the fact. Nova's AR overlay feature, which you can see in this slide image, allows you to see your design before you print it and actually enables you to have a much easier and accurate alignment process with pre-existing features on your substrates. With Nova, you have flexibility on the substrate types you can use and how you want to mount them. You can mount flexible and stretchable substrates to Nova using the included vacuum module and built-in vacuum pump. And you can mount rigid substrates using Nova's rigid mounting fixtures, or you can even create your own custom mounting fixtures to secure your substrates to Nova's base plate. And that's Nova. Now that we have an overview of Nova, let's dive into some materials, substrates, and methods for printing sensors specifically for the field of soft robotics. While there are many inks on the market that are applicable to printing electronics for soft robotics, I'll focus on the ones that we currently stock on our store. And these are some of the flexible inks that we stock. The first is ACI's FS0142. It's a silver-filled conductive ink for flexible electronics. It's a high conductivity material for higher power or current density applications. It has superior performance withstanding flexing and creasing, and it can be soldered to with low temperature solder pastes. Next is ACI's FC3203, and this is their flexible carbon conductor. It's a high conductivity carbon conductor and exhibits limited resistivity change when associated with bending and flexing. Carbon inks are great because they offer high thermal stability at a lower cost compared to silver. Their chemical inertness makes carbon suitable for printing resistors and conductors on non-conductive materials like plastics, ceramics, and paper. And they're often layered between silver inks to protect them from silver migration. They offer similar benefits as silver in terms of adhesion, ease of printability, and substrate compatibility. We also have VFP's silver electron ink, and this is another conductive ink for flexible electronics. The main advantage of this ink is that it can be used in thermoforming applications and has a good resistance to overmolding. It maintains conductive stability over time after annealing and elongation. So if your application requires that, this might be an ink to consider. And finally, we have VFP's ECV003, and this is a UV curable green tinted flexible and dielectric varnish. And this acts as a great electrical insulator for printed circuits. You'd want to use this ink to provide insulation and protection for functional ink layers in a multi-layer print. Next, we'll dive into the stretchable inks for soft robotics. All of these inks specifically are compatible with one another as they're in ACI's stretchable line, and they can actually be used for multi-layer print stack-ups. They can be used on stretchable substrates and create functional circuitry. ACI's SS1109 is their silver filled conductive ink for printed stretchable electronics, and these can be used to print interconnects for devices on elastomeric substrates. After drying, it has excellent conductivity and offers excellent elongation and flexibility. It's been formulated specifically to be printed on TPU, which is a stretchable substrate, and it's used in stretchable electronics, e-textile applications, and it's for powering components and devices and carrying signals from embedded devices and sensors to your controls. ACI's SC1502 is a carbon-filled conductor, again for printed circuitry and devices on substrates like TPU, stretchable substrates. It can be dried at low temperature, so it's good for accommodating more sensitive substrates and devices. After curing, it has good conductivity and offers excellent elongation and flexibility. Again, it's been formulated for use specifically on thermoplastic urethanes or TPU, and it's specifically useful for printing over silver layers in sensor applications, again, to limit silver migration. Lastly is ACI's SI3104, and it's a white printable thermally cured ink that is stretchable after curing. It's specifically used as an insulator or can be used for crossover dielectrics. After curing, it has excellent durability, flexibility, and a high insulation resistance. It's designed for printing on TPU and again is fully compatible with the other two inks from ACI's stretchable line. Moving on to our substrates, let's touch on some flexible substrates that you can use on Nova. So we have specifically Normandy's PET. PET is a transparent film, and this one is engineered for precision material deposition in flexible electronics. It's heat stabilized, so this minimizes shrinkage and ensures that the substrate maintains dimensional stability during high temperature curing processes, which is needed for ink. And PET is a very cost-effective material that you can use when you're prototyping your flexible circuitry. We also carry Polyonics XF102 polyamide. And polyamide is superior for high-performance flexible electronics. And this is mainly due to its excellent heat resistance, its mechanical durability, and its chemical resistance. So this makes it ideal for more demanding applications like aerospace or wearables. And the final substrate I want to touch on is paper. Nova can actually print on paper-like substrates. And the reason you use paper is because it's a low-cost, flexible, and sustainable substrate for printed electronics, like sensors and circuits used in applications like smart clothing, for example. Paper is lightweight, it's flexible, and it's breathable. And that's crucial for comfort in wearable applications. It's also a sustainable option for single-use devices. So paper-like substrates might be something to consider. For stretchable substrates, some of the stretchable substrates that you can use on Nova for printing stretchable electronics include TPU, Panasonic's Biolex, and Fabric. So the TPU that we stock is Intexer's TE11C TPU, or thermoplastic polyurethane. And it's a highly stretchable film engineered for stretchable electronics. It's compatible with a variety of stretchable materials as well as Nova, and it ensures robust adhesion for circuits requiring repeated flexing. TPU as a substrate has a high level of recovery, and it's designed for printed circuits requiring repeated flexing and stretching. TPU that we stock has a melt layer adhesive, and that allows it to be bonded securely to fabrics like polyester and nylon by heat lamination, as we've seen Nick demonstrate in his one project. And TPU is perfect for fitness, health monitoring garments, stretchable sensors in e-textiles, medical wearables, and as we've been talking about today, soft robotics. We've also printed internally with Panasonic's BLX. This unique material is based on a proprietary thermoset non-silicone polymer, and this provides improved performance when compared to TPU. It has good elongation, ultra-low hysteresis, and higher temperature resistance and high environmental stability. Again, it's perfect for creating sensors for medical wearables, e-textiles, and soft robotics. And finally, I want to highlight that Nova can actually print directly on fabric, which can be useful for developing sensors and electronics in wearables, as well as coverings for soft robotics. There are a couple of things to keep note when printing fabric on Nova. We find that backing the fabric with material like Kapton tape allows the vacuum module to apply suction to the fabric. If it didn't have that backing, it wouldn't be held down. And then finally, we find that fabric also requires multiple passes of ink so that all that ink can soak into the fibers and build up a functional layer resistant to that stretching and deformation while still maintaining conductivity throughout the traces. All of these substrates that I've just talked about, the flexible and stretchable, are mounted to Nova using the vacuum module. So this porous titanium plate that applies suction across the surface of the substrate. Next, I want to talk about one of the main workflows in Nova that really enables the development of sensors for soft robotics, and that would be our workflow plan. This is a feature that we released earlier this year, and it unlocks multi-layer printing with Nova. Plan gives you greater control over how Nova is printing your designs and enables multi-layer printing. Specifically in Plan, you can set up multi-layer workflows by importing your multi-layer designs into Plan. You can then visualize all of the layers and how they'd stack up together. You can change that order if you'd like in the software. Plan will automatically generate probe points, specifically at overlaps and layer height changes, which is a requirement when you're printing multiple layers of ink. And then finally, Plan creates efficient height mapping for faster file processing to get you printing your sensors faster. When printing your design in Plan, you have even more control. You can edit your print job and layer order. You can visualize toolpaths and probe points for quicker iterations and customizations. You can reorder your features for consistent printing results. You can remove unnecessary elements from your designs for simpler printing processes. And finally, you can save and reuse your print settings for easy and consistent reprints of your designs. So you can iterate over and over again with consistency. Some of the projects that our applications team done, I want to highlight because many of these showcase functional sensors that can be printed with Nova, and these can be applied to soft robotics. Along with printing the actual sensors, this specific project, connecting flexible and stretchable substrates to printed circuit boards, showcases the many ways that these flexible and stretchable sensors can then be connected to a classic PCB for reading their outputs. Going in order, number one, the circuit highlights, it consists of a touch electrode, so that large square pad at the top, and then a trace leading down to the smaller contact region at the bottom. Once printed and cured, this substrate was covered with Kapton tape to insulate and stabilize the touch interface. But when a finger or a conductive object approaches the pad, it increases the capacitance of that electrode relative to ground, and then it can be a readable output. This specific sensor was printed on PET using ACI's FS0142 flexible silver ink. The second circuit consists of a piezo-resistive element, as well as a fine modeled trace that serves as an interdigitated electrode. When pressure is applied, the carbon film compresses and the resistance drops between the interdigitated silver electrodes. It was printed on PET with ACI's SS1109 silver stretchable and their carbon flexible ink as well. Number three is a flex sensor, and that consists of traces that form an electrically resistive sensing element. So that's the carbon, the black carbon traces you can see. And when the sensor bends, the carbon traces deform, and that increases the circuit's resistance. This resistance change is measured through the silver interconnects printed with ACI's SS1109 on PET, and it's used to quantify the degree of flex or curvature. So in the image number 3, we can see that flexing of that sensor causes reading, and that would be through the LED on the board. And the last sensor we can see in Section number 4 is a serpentine-style resistive strain gauge. It was printed on TPU with ACI stretchable carbon ink, and as the material undergoes stretching, the resistance of the circuit changes, and then this change can be detected. All of these sensors can be applied in a soft robotics application. And if you're interested in learning more about them, more details of the project can be found on our website under use cases and connecting flexible and stretchable substrates to printed circuit boards. The next project I want to highlight is more applicable to a soft robot, is still applicable to a soft robotics application, but would be more of the inverse. This is the strain gauges printed on TPU for remote hand control. So an inverse of this would be strain gauges on a robotic hand instead of on a glove, acting as a controller. So this project was done by our applications team and demonstrates how you can print stretchable silver ink onto TPU as a strain gauge to detect movement and measure movement and deformation. Again, this would be in a soft robotics application. These sensors would be on the robot hand versus on one of our team members' hands. Again, more details on this project and many others our team has done can be found on our website under use cases. And finally, I just want to highlight again Nick's project that showcased soft robotics specifically and his soft robotic gripper that he developed using Nova. It incorporated 2 different types of printed sensors to measure the movement of the gripper and the gripping strength. Thank you for listening to me talk about Nova and how Nova can be applied to soft robotics. We're going to move into a Q&A section. So I want to go back and highlight some of the questions that we had, and then if we have any more, please type them in the question and answer chat. I'll try and answer some as well as Nick and our team. So let's see what we have. What is the maximum bending angle of the printed substrates? So I think, Nick, this was talking about in your, with the gripper, was there a maximum bending angle for
No,
what you
not
printed?
like I think that oftentimes when you're dealing with these types of substrates, you think about minimum bend radius. And so for a 100 to 150 micron thick substrate, you could kind of think that the bend radius is about the minimum bend radius would be about 1 millimeter if you're thinking 5 to 10 times that thickness. So I don't see there'd be like a really strict maximum bending angle for this. And if you're talking about that soft robotic gripper, it would be close to like 100 degrees maybe in the best case. So yeah.
Yeah. I think it
I
highlights
hope that answers
also,
it.
yeah, one of your concerns was the fold line. So
Mm.
did you have a chance to test that at all? Or did you move
Yeah,
on?
so we did actually test that. And the hard part was that we really couldn't get that fold line to crease out really well. And so when you bent that, the bend radius would actually be a lot lower than that 1 millimeter if you heat press that over on the other side. And so if you kept that 1 millimeter, we tried using like a metal dowel rod to preserve that bend radius. And we thought that the packaging didn't necessarily look as sleek in that form factor with that big crease on that one side.
Yeah, for sure.
Hmm.
What is the curing process of these inks? How does the ink get cured? So I can answer that. All of our inks are mainly cured in a box oven. So they go in, depending on the material, the curing information is on the data sheets, but generally over 100 degrees Celsius, and they're cured in a box oven for generally 5 to 15 minutes. Specifically, this isn't in the question, but for multi-layer printing, the process you'd need to cure every layer of ink before depositing a new layer, especially for material changes. So you need to be printing on cured layers of ink so that they don't mix. Next, can the ink print on glass material and the adhesiveness been proven? So yes, ink can be printed on glass. It depends on the ink. There's many different formulations again. So some of them are designed to print on substrates like glass and ceramics. Adhesiveness would be generally in the data sheets, the technical data sheets from the manufacturers of the ink, and they would have specific testing that they've done. So you'd have to consult the data sheet of the specific ink that you're interested in for that information. Is there ink around for flexible material which does not exceed excessive curing temperatures for delicate materials, sub 100 degrees Celsius? Are there alternative curing processes, longer curing time, cooler temperature? Yeah, so we do find that some inks are designed for lower temperature curing. Many inks we've found that you can cure at a lower temperature for a longer period of time, and that allows them to be just as functional while reducing the temperature required. So for those substrates that need it, you can do that. This is a Nick question here. Could you please elaborate on the core computation of the soft robotic system integrated with flexible electronics? How complex is this computation? What are the hardware complexities for performing computations using soft robotics in terms of hardware footprint, area, power, and energy consumption?
Okay. Okay. So yeah, a little bit of a complex question in some ways, but what you'd probably have to do is you'd create a simplistic model, and you'd abstract the system that you could then run on edge. So like actually on the system itself, as opposed to trying to compute that on a larger computer elsewhere. So you'd have a basically like a linear approximation of for a given pressure or current, how does this robot deform, or what do you think it's deforming like? And then you'd basically try and create some sort of a loop with the sensor feedback. So you have your predicted state, and then maybe your sensor is saying, no, we haven't reached contact yet, or we haven't applied a certain amount of force. And then you basically bring that into maybe a PID or some other type of control system. I mean, that's a pretty basic system. And then with that sensor reading, you could then kind of compute what your error is and then account for that. I think that's probably the easiest way to answer this.
Yeah, for
I
sure.
don't think there's really not any feasible ways right now to try and actually solve what the soft robot is doing in like a more FEA simulation approach. NVIDIA is getting close, but I still don't think that's really attainable right now.
Yeah, and I think in terms of the second part of that question for the hardware complexity of performing these computations, this is one of the big kind of problems that people try to solve is how do we integrate the computation part. So oftentimes with soft robotics, if it's a wearable, you want to avoid having wires connected. So that would be decreasing the footprint, the size of a rigid computer module and having some wireless computation. For like a robotic arm, you're less worried about that. So you could have a physical wire going from your soft robotic platform to a computation model. So for the wireless, obviously energy consumption and power are a big concern. How do you reduce the footprint and have powering via wireless way through like a battery? For wired connections through an actual like robotic arm, that's less of a concern. You can power directly through that. Could you please comment on the biocompatibility of the conductive inks and substrates, for example, implanted devices? So, not specifically, I won't talk specifically about implanted devices because I don't have that expertise. But in terms of biocompatibility, there are inks that are biocompatible. We do have and carry a silver chloride ink that is specifically designed for its biocompatibility. So there are inks out there that are biocompatible, mainly for less for implanted and more for like contact. So one of our applications projects was a heart rate monitor. So that would be designed to be biocompatible and to be stuck onto your skin and body. Are these inks only suitable for Nova? Can it be used for spin coating or spray coating on TPU? So these inks are not only suitable for Nova. The similarity that all these inks have is they're actually mainly used for screen printing. So the benefit of Nova is that you can avoid the screen printing process while you're creating your designs, while you're iterating, while you're prototyping. And then once you have a design that you're happy with and you want to move forward, you can then take it to a screen printing process, and that would be kind of going into a mass production route. For spin coating and spray coating, I'm not 100% sure. Definitely not spin coating, as spin coating requires a super low, very low viscosity fluid and is more for like thin film in the thin film industry. Spray coating, again, probably these materials are not suitable for that, but it would be definitely for screen printing is where these materials would translate more into. Nick, this is a question specifically for you. What was the substrate of that printed silver that was attached to that soft robotic? Was it attached thermally?
Yeah, so that was the in Texar, the TE-11C. And so that was attached thermally with a heat pressing process. So just a standard, almost like a apparel heat press that you can find anywhere. And then if you basically press the backside of the substrate onto some fabric that is compatible, it'll thermally bond and create a very good bond. It won't really delaminate at all.
I'm going to go through a couple more questions here as we're getting close to the end of our time. So let me pull a couple. Is there any restriction for surface roughness when printing on substrates? I would answer this, it depends. But in general, no. Because we're printing above the surface of the substrate, so our nozzles on average hover around 60 microns off the surface of the substrate, and we're depositing ink based off of that. Generally, surface roughness shouldn't affect the printing quality. You may need to maybe print 2 lines of ink, like deposit more ink material so that you're filling in those valleys, let's say in the surface. But in general, no. Obviously, you can get crazy with your surface roughness, but I'll say in general use case, no. Do these sensors behave in a linear way? Do these sensors behave in a linear way? If so, can we depend on the sensors for repeatable results? Would fatigue, so through stretching or flexing, I assume, affect their performance over time?
Okay, yeah. So in most cases, no. These sensors won't necessarily behave in a linear way, depending on how what type of sensing modality versus like capacitance versus resistive. Um, Usually there's a inverse square or a logarithmic trend to them or an exponential trend. They're really it's very hard to set up these systems to be a perfectly linear way. So usually you have to calibrate it in order to get a linear approximation. And then for the repeatability, that kind of depends on how much strain or stress you're applying to them and the hysteresis of your material and ink. So certain inks might have some internal hysteresis with their conductive filler material, not necessarily silver inks. And then certain substrates, if they're elongated to a certain point, they might plastically deform. So then you're not really going to get repeatable results. Or if you're maybe doing like a step impulse that's really fast and it's kind of a little bit faster than the relaxation time of your material, then you can kind of get into a hysteresis process and you're kind of in a walking cycle. So then your repeatability goes out of the window. So it's really material dependent and how far you're kind of pushing these materials in terms of their fatigue and repeatability.
The last question I want to highlight here, do you allow research institutions to test their ink printability with Nova as in collaborations? So this is an interesting one. We do have a printing as a service, as well as we have done where we've gotten ink samples in from different people and printed with their ink to see if Nova is a good fit, if it will work on Nova. So I would suggest that if you have a custom ink that you'd like to see if it'll work on Nova, reach out to our sales team and they will kind of walk through the process of how we can get your ink to see if it will be a good fit with Nova. That's all the time we have for questions. So thank you, Nick, for doing some rapid fire questions with me. The last thing I want to highlight here before we end our webinar is our flexible and stretchable bundles. So we do have some bundles that will set you up for printing flexible and stretchable electronics with Nova. And specifically when buying these bundles, there's a significant discount compared to buying them individually. So for our flexible bundles, these contain the flexible substrates we stock, PET and polyamide, as well as dispensing tips and a variety of their flexible inks depending on the bundle level. The same with stretchable. These come with TPU, dispensing tips, and a selection of ACI stretchable inks. The variety of those increasing as you increase the level of the bundle. So those are available on our store. And I'd suggest that you check them out if you're interested in printing flexible or stretchable electronics with Nova. So I want to say thank you for sticking around to the end of our webinar. As promised, the $2,000 discount code for your purchase of Nova is Robotics, so you can use that. If you are interested in purchasing Nova or you'd like more information on how Nova could be useful to your application or use case, please reach out to our sales team by emailing them at sales@voltera.io, or you can call the number on the screen there. They'd love to discuss if Nova would be a good fit for you. And you can find more information about all of our printing systems on our website, www.voltera.io. Yeah, thank you for tuning into our webinar on Software Box today. I hope that you've learned something. I know I have. Big thanks again to Nick for joining us. We really appreciate your insight into the field of software robotics and your expertise.
Thank you very much for having me.